Let's go ahead and do another problem. A racquetball with a velocity of 13.2 meters per second strikes a wall perpendicularly and rebounds in the opposite direction with a velocity of 12.1 meters per second. If the ball is in contact with the wall for 0.008 seconds, so 8 thousandths of a second, not a lot of time, what is the average acceleration of the ball during this time? All right, so the first thing we want to do is draw a simple physics diagram. And for this problem, my diagram is going to look a little bit different. So stick with me. Here we go. This is going to be the wall right here. And I'm going to go ahead and add a little shading on my wall just to make it more obvious. That's just the way I like to draw it. You can draw it with just a vertical line if you want. And I'm going to make the racquetball go this way initially. Again, it doesn't matter if you made the racquetball go that way, it would still work out to be the same. But let's go ahead and make it go to the right. So here's the racquetball. It's going to the right. There it is right there. And the initial velocity is going to be 13.2 meters per second. And notice how it's traveling perpendicular to the wall. It then bounces off the wall backwards. Now I'm going to draw it like this. Now in real life, if this was perfectly horizontal, the ball would bounce back perfectly horizontally in the same direction. But then my arrows are going to overlap here. Remember, this is a simple physics diagram. This is not 100% reality, right? We're trying to model what's going on here. So this is how I'm going to model it. This is my racquetball going in one direction. And then even though it would come back at exactly the same, along the same arrow here, I'm going to draw it down here. So my final velocity is 12.1 meters per second. And notice it's a little bit less because our ball lost some energy. It lost some energy of motion. We'll talk more about that later here. But the wall's got a little bit of friction. The ball lost some energy there. All right. Anyhow, time 0.008 seconds. So a very small time that it's actually in contact with the wall. And we want to figure out the average acceleration. So that's my unknown, trying to figure that out. Now, we got to be a little bit careful here with a problem like this. So first of all, let me just kind of walk you through what's actually happening here. I got a racquetball, and it hits the wall. We need to identify where this problem actually begins. And the problem actually begins just when this racquetball, just when it starts to touch the wall. And at that point, it's going 13.2 meters per second. And then pretty much what's going to happen here is the racquetball is going to get squashed, squashed, squashed. And it's also at the same time, what? Slowing down, slowing down, slowing down, stopping. And then as it kind of expands itself again, it's actually going to speed up, speed up, speed up, speed up, and leave the wall in the opposite direction. So keep that in mind. That's what's going on. Now, one more thing. If I just leave it like that, I'm going to get the problem wrong. So I did this on purpose because this is what a lot of students will do, and they'll get the wrong answer. And there's a very small thing that they're forgetting here. Notice that my initial velocity, and I like to make the direction of motion, the initial direction of motion, I like to make that my positive direction. So I'm going to make to the right the positive direction. Notice the ball, as it returns, it's coming back to the left. Yeah, and velocity is a vector. It's got a direction. So what I need to do is I need to make this velocity negative. Yeah, and again, that doesn't mean that that velocity is less than 0. It just indicates that negative sign indicates that my velocity at this point in time is opposite the direction it was initially. That's all it means. The ball's now going 12.1 meters per second in the opposite direction that it originally was going. All right, once we've done that, once you can wrap your mind around that, it's really not that difficult of a problem from this point on. So average acceleration equals change in velocity over time. Now go ahead and expand this. Don't do it in your head. Do it on paper because there's less chance that you'll make a mistake if you write it down. Velocity final minus velocity initial over time. Because remember, change in velocity is really that in disguise. All right, now we can go ahead and substitute in. I'm looking for the average velocity. The final velocity is negative 12.1 meters per second minus the initial velocity of 13.2 meters per second divided by the time, 0.008 seconds. And notice we're going to get a negative number. When you do the math here, it comes out to negative 3162, negative 3162.5 meters per second squared. And that's a huge acceleration, it really is. Now if I use my significant digits and I do all that sort of thing, I only got one significant digit here. So if I round this off to one significant digit, it's literally going to be negative 3,000 meters per second squared. So that'll be my final answer when I round off. All right. But if you're not using significant digits, you could leave it like that. But if you're using significant digits, that would actually be the final answer. And what does this actually mean? Negative 3,000 meters per second squared. Yeah, so its velocity is changing by 3,000 meters per second each and every second. There's a huge acceleration going on there. If that was you, your body would not be able to take that type of acceleration. It would just get ripped apart. But the racquetball can actually take that. So let's go ahead and talk about this just a little bit further because I want you to really understand what that answer means. Now, this is the acceleration. Notice it's negative. Look at the velocity here. It's positive. Whenever the velocity and the acceleration have opposite signs, the object's slowing down. So just think about that. The velocity is in that direction, and the acceleration is in the opposite direction. So the object is slowing down because the two are actually in opposite directions. Now, notice when the ball actually rebounds and returns. Now I've got a negative velocity and a negative acceleration. All right? So what's actually happening here is the ball, while it's in contact with the wall, is actually speeding up in the opposite direction. Remember, whenever velocity and acceleration have the same sign, positive, positive, or negative, negative, like in this case here, the ball's actually speeding up. But in this case, the ball is speeding up as it leaves, as it rebounds from the wall. Now it's still in contact with the wall because it goes from 0 and then it speeds up, speeds up, speeds up, speeds up to the left. And just when it leaves the wall, that's how fast it's going. Now once it leaves the wall, it's not going to speed up anymore because there's no force, there's no wall pushing on it anymore. So it's going to kind of leave the wall at negative 12.1 meters per second, and it's going to stay at that velocity until it bumps into something else. All right? So that's what's going on there. You really got to kind of think about that a little bit, and it's nice to actually understand your answer. Just don't get an answer, put a box around it, I'm done. Right? Try to understand your answer. Does it make sense? Do I really know what's going on there? Always try to do that. Make an effort for that. All right, that's it for this problem.